Okay, so I'll lecture some more on 3.6, give you a quiz. I might sneak in just very bare beginnings of 3.7. 3.7 is actually not that long of a section. I should be able to finish it just on Monday. Okay, and everybody knows next Thursday is a flex day. There's no school on that day for you guys. So teachers have to show up, but you don't. All right, so I'll go back and do logarithmic differentiation. I'll speak very briefly about 3.7 and then give you the quiz, and then we're done for the week. Right? In fact, looking ahead to 3.7, there aren't that many problems. 7 to 19 odd is not that many. So I should be able to knock it off just Monday, but we'll see. Okay, so back to logarithmic differentiation. I did some yesterday, and I'll review the highlights of it, but do some more now. So page 221, 3.6, steps in logarithmic differentiation. So I didn't show this to you before, showed it to you today now, but you sort of got the idea. So you take natural logs of both sides of an equation, y equals f of x, and use the laws of logarithms to simplify. So you want the right-hand side to be nice, so to speak. You differentiate implicitly with respect to x. It turns out the left-hand side is always going to be the same thing. It's going to be 1 over y dy dx. And then solve the resulting equation for y prime or dy dx. Okay. So that's what we went through. And then I want to re-emphasize this thing at the bottom of the same page, 221. Okay, so what happens if you have these different scenarios of exponents? Okay, so constant to a constant, variable to a constant, constant to a variable, variable to a variable. Okay, so if you have a constant raised to a constant, it's still a constant, so its derivative is 0, right? So like the derivative of 3 to the 74th power, don't do anything, the derivative is 0. Okay, now variable base constant exponent, like f of x to the nth power, okay, that's the power root. So n times f of x to the n minus 1, and then by the chain root times f prime of x. Switch it around, you have a constant base but a variable exponent, like b to the g of x. The derivative is b to the g of x ln b for exponential functions, and then times g prime of x. But if you have a variable to a variable, f of x raised to the g of x, then you do this logarithmic differentiation stuff. Okay, so here's a nice summary. And, you know, it's up to you if you want to put all that in your cheat sheet. That might take up a lot of space, but this covers all the situations. Okay. So as you can see here, right, variable raised to a variable, don't do the power root, don't do the exponential root, do logarithmic differentiation. Okay. All right, so let me show you those again. Okay, now I showed some of these to you yesterday, so I'm just going to fly by the concept again. So for 41, y equals the square root, right? So it's almost like saying it would be very nice if I had an ln to make it nicer. So just take the ln of both sides. Okay. Then use your properties of log to make it nicer. Square root means raising to the 1/2. 1/2 comes in front. Ln of the quotient is the difference of the logs. Ln x minus 1 minus ln x to the 4th minus 1. Okay, now the left side is always going to be 1 over y dy dx. Never changes. And then differentiate the right side. 1 over y dy dx is 1/2 blah, blah, blah. I showed that to you yesterday. And then the last step is to multiply both sides by y. Okay, but you don't leave it as y. You write what it originally was. So there's the 1/2. Here's y. Y was the square root of x minus 1 over x to the 4th plus 1. And then you have this extra factor of 1 over x minus 1 minus 4x cubed over x to the 4th plus 1. Okay. All right, and then, yeah, I showed you this again. If you have a variable to a constant, like x squared, variable to a constant, derivative is 2x. But if you have a constant to a variable, 2 to the x, the derivative is 2 to the x ln 2. But if you have a variable to a variable, like x to the x, you do logarithmic differentiation. Okay, so here's the highlights of how to differentiate x to the x. Take the natural log of both sides. that allows you to bring the x down. So ln y equals x ln x. Okay. Then you differentiate implicitly, but the left-hand side is always the same. 1 over y dy dx. Okay, this looks like a product rule. So first x times the derivative of the second derivative ln x we now know is 1 over x, plus the second function ln x times the derivative of the first, which is 1. This cancels out, so I have 1 plus ln x. Now just multiply both sides by y. That step is always going to be the same because you're trying to isolate dy dx. But you don't leave it as y. What was the original y? X to the x. Okay, we usually sneak it in front. Okay, so sneak in y, x to the x, times this extra factor, 1 plus ln x. Okay. All right, so I'll show you some more of this logarithmic differentiation, and then I'm pretty much done. Okay, 49, tangent of x raised to the 1 over x. Okay. So all of these problems at the very end look like a variable raised to a variable, right? So all of these, you'd have to do this logarithmic differentiation stuff. Okay, so take the natural log of both sides. So ln. Once you have the ln, this 1 over x comes down, right? And if it's going to be 1 over x, you might as well just write it as the whole thing over x. Okay, so see this 1 over x times ln tan x, just have it divided by x. It's the same thing. Okay, now I differentiate implicitly. Okay, again, the left-hand side is always the same thing. 1 over y dy dx. Okay, and then after that, you multiply by y. Okay, the derivative of the right-hand side is going to be a little bit tough. It looks like a quotient rule and a chain rule on top of that. So bottom x times the derivative of the top. So what's the derivative of ln tan x? Well, first you go 1 over tan x. And then by the chain rule times the derivative of tangent x, which is secant squared x. Okay, so again, this is the bottom times the derivative of the top. X times derivative of ln tan x is 1 over tangent x. And then times the derivative of tangent x, which is secant squared x. Okay, minus the top, ln of tangent of x, times the derivative of the bottom, but the derivative of x is just 1, so I don't have to put anything. And it's all over x squared. Okay, that's essentially it, except now you multiply both sides by y. You want to isolate the dy dx. So the left side calculation is always the same because it's always going to be an ln y. Then you go 1 over y dy dx, and then multiply both sides by y. So dy dx is equal to y, but I don't write y. I write what it's equal to. The original y was tangent of x raised to the 1 over x. And then this new thing. And the only thing I made a little bit nicer is this is 1 over tangent, right? What's 1 over tangent? Cotangent. So x, cotangent x, secant squared x, minus natural log of tangent x, that whole thing divided by x squared. Okay. So that's all that. Okay, so that's problem 49. Okay, don't look at this yet. This is starting the next section, actually. Okay, but I was going to do a couple more of the logarithmic differentiation type. Okay, so I'll make this disappear for now. Okay, go back to 39. Now, 39, you can actually do this just by the product rule. You'll get the same answer. But they say use logarithmic differentiation. Okay, so even though you can do it by the product rule and the chain rule, it says use logarithmic differentiation, which means take the natural log of both sides, ln, ln, right? Because once you do that, you get to use your property of logs. Okay? So for instance, I see the natural log of a product, something times something. So it's a natural log of the first plus the natural log of the second, property of logs. ln of a times b is ln a plus ln of b. Okay, and then do you recall what happens to these exponents? When there's an ln, they both get to come down in front, which means I can avoid doing, chain rule. So now ln y equals 2 natural log of x squared plus 2 plus 4 natural log of x to the fourth plus 4. Now I'm ready to differentiate implicitly. Okay. Well, the right-hand side has no y, so it's just a regular derivative. The left-hand side never changes. It's always 1 over y dy dx. You can pretty much bank on it whenever you do this logarithmic differentiation stuff. And you can tell what's going to happen after that. Just multiply both sides by y. But in the final answer, don't write it as y. Write it as what it originally was. Okay, so now I take the derivative of this. So this side's always 1 over y dy dx. Okay, so 2 times 1 over x squared plus 2. Then by the chain root times the derivative of this, which is 2x, plus 4 derivative of ln x to the fourth plus 4, 1 over x to the fourth plus 4. Again, by the chain root times the derivative of the inside, that's 4x cubed. Okay, so clean up this extra factor. 2 times 1 times 2x is 4x over x squared plus 2. 4 times 1 times 4x cubed, that's 16x cubed over x to the fourth plus 4. Okay. And yeah, then the last thing is to multiply both sides by y, but you don't write it as y, write the original. And by convention, we usually put the y in front. So at the final stage, put the y, the original y goes in front. So x squared plus 2 squared, x to the fourth plus 4 to the fourth, and then times this new thing, 4x over x squared plus 2, plus 16x cubed over x to the fourth plus 4. And you can stop there. That's pretty much it. You're done with that one. Okay, so this is the answer. You could do more algebra. I don't feel like it, and you probably don't feel like it either. But if you did more algebra, you would get the same answer as if way back at the beginning, and you didn't do any of this logarithmic differentiation stuff, and just did the product rule. Okay, you would have gotten the same answer. It'd be equivalent. All right, then the last one was 45, and then I'm done. I'll do some introductory remarks about the next section, and then I'll give you the quiz. Okay, so for 45, y equals x raised to the sine of x. So again, that fits the category of variable raised to a variable. So when you have a variable raised to a variable, do logarithmic differentiation. See, I don't want that sine x way up there. How do I get it down? By doing natural log. Okay, so ln both sides. Once I do that, sine x comes down. So ln y equals sine x natural log of x. Now I differentiate implicitly. But the left side's always the same. It's always going to be 1 over y dy dx. And then the last step is to multiply both sides by y. So it's not just a matter of figuring this out. I've already multiplied by y. As you can see, I sneak the y in front at the end. So this is a product root. Sine x times the derivative of ln x, 1 over x, plus the second function, ln x, times the derivative of the first function, derivative of sine x, cosine x. All right, and then, yeah, multiply both sides by y. So that cancels out. dy dx is y, x sine x, x raised to the sine x, sorry. And then I just copy all this. The best way to write this is sine x over x, and then plus cosine x natural log of x. Okay, so that's pretty much it for that. Okay. All right, so I am done, folks, with 3.6. So we're right on schedule. Okay, 3.7, what is it about? So let me just talk quickly about what it's about. I know some of you may have put something in the chat. I'll address that and then go straight to the quiz for the rest of the class period. Okay, so 3.7. The topic is rates of change in the natural and social sciences. Okay, you're going to get some word problems here. Don't want you to get scared about that, but where do derivatives occur in real life? Okay, they could occur in, they got some examples here from chemistry, page 227. They got biology, 229, obviously physics. Some of this stuff. Economics, page 231. Okay, so you're reading a lot of these words. They're word problems, but if you get around the word problems, you're basically still taking derivatives. Okay, so like for 7, we talked about this before. You have some function. The first derivative is velocity, right? Second derivative is acceleration. So that might happen. Okay. You have some applications involving, I don't know, making computer chips, I think. Yeah, so like number 11, you're making computer chips. Okay. Doing with some physics, throwing something up if you happen to be on Mars or something like that. Okay. Rates of change. Okay, average rate of change, you're blowing up a balloon, and you want to know how fast it's changing and so on. Okay. So these are some of the things that we're doing. Okay, so once you get through all the words, you basically have a function. You want to differentiate the function. What am I trying to take the derivative of, and stuff like that. Okay. So that's basically what's happening for sections 7. There's really no new formulas. Okay. We are going to revisit, velocity is first derivative of a distance function. Acceleration is second derivative. You had it before. I'm not going to write that down because you don't really need it now. It is going to be in the video, but when we get to it, we'll use it. Okay. All right, but that's pretty much about it. Let me check the chat real quickly. If there's anything. So, nope, doesn't look like it. Okay, so I think we're done. All right, so I will get you started on the quiz, and Prasanna and I will come around and visit as usual. So I'll put you in your breakout rooms as usual. The usual spiel about quizzes is it's not due until Monday at 12:10, but if you submit it early and something's not right, I have a chance to, maybe make a comment about it and get back to you. But if you don't submit it until, 12:09 on Monday, obviously I don't get a chance to do that. Okay? All right, so get your cameras out and be ready for the quiz. Then I'll put you in your breakout rooms, and then you can work on the quiz, and Prasanna and I will come around as necessary. Okay? Okay, so here we go. So take a picture, and I'll blab about it for a moment. So in each case, find the derivative dy dx. Okay, number 1, f of x is sine of cosine of tangent of x. Oh boy, so that looks like 1, 2, 3 layers of the chain rule. Number 2, y equals 2 raised to the x squared secant of 3x. So it's an exponential function, but the base is not e, the base is 2. That makes it a little bit harder. And look at the exponent. The exponent is a product, and there's a secant, and there's a 3x. That makes it a little bit tougher also. Number 3, it looks like x's and y's are all mixed up, so that looks like the implicit differentiation stuff. Okay, and number 4, ln x squared plus 4 minus x over x plus 1. So that looks like a, chain rule, and that looks like a quotient rule, I suppose. Okay, so give that a shot. Get started for a moment. Give me a few seconds to set up the breakout rooms, and I'll have you join the breakout rooms, okay? And then that'll do it for today and the week, and have a good weekend. Okay, so get started. Let me set up your breakout rooms and join your breakout rooms, please. Okay, you should have an invitation to join your breakout room. So can everybody join your breakout room now, please?